Hey, welcome to The Explainer. You know that device you're watching this on right now? Your phone, your laptop? It really feels like magic, doesn't it? Well, it's not. And today, we're going to pull back the curtain and show you the super elegant, logical, and just insanely fast process that's powering every single thing you do on it.
No, really. Just stop and think about it for a second. You click an icon, and this whole universe of activity just explodes into life, all in a fraction of a second. How? I mean, what is the very first step in that chain reaction? That's the exact journey we're about to go on.
Okay, so let's start with the blueprint. Now, you might think your smartphone and some, massive government supercomputer are worlds apart. But here's the thing. They share a secret. Deep down, they're both built on the exact same really elegant design, a master plan that's been guiding pretty much every computer for decades.
And this is it. It's called the von Neumann architecture. It was dreamed up by the genius mathematician John von Neumann, and it's the master plan for everything. Now, it lays out all the essential parts, but its real magic trick is this one simple idea. The instructions, what to do, and the data, what to do it with, are stored together in the same memory. That one idea is what makes a computer a flexible, all-purpose machine and not just a glorified calculator.
So, based on that blueprint, let's meet the core team inside your machine. You've got the CPU, right? That's the brain. It does all the actual thinking. It uses memory, or RAM, as its short-term workspace, like a scratch pad for whatever it's working on right this second. For everything else, you've got mass storage. Think of that as the long-term filing cabinet. And then you have input devices like your keyboard and mouse, which is how we talk to this whole team. And it talks back to us through output devices like your screen. These parts aren't a constant, high-speed conversation with each other.
All right, so we know the players. Now let's actually follow a single command on its incredible journey. What really happens when the brain decides it's time to do something? Well, it all boils down to this simple, endlessly repeating cycle.
This is the machine cycle. You can think of it as the fundamental heartbeat of your computer. It's a four-step dance: fetch, decode, execute, and store. And your processor does this dance billions of times every single second. Yeah, you heard that right. Billions.
So everything kicks off with fetch. The CPU's first job is to reach out to that short-term workspace, the RAM, and grab the very next instruction on its to-do list. But how does it know where to look in all that memory?
So how does it find anything? Well, think of RAM like a giant football stadium. Every single seat has a unique number, right? Section, row, seat. Well, in a computer's memory, every single location has a unique address. And a little part of the CPU knows the exact address of the next instruction it needs. So it doesn't have to search, it just goes right there and grabs it. Okay, so the instruction has been fetched. Now the CPU needs to figure out what it means and then, well, do it. This is the decode and execute phase, and it requires two specialists inside the CPU to work together like a well-oiled machine. Think of the control unit as the project manager. It looks at the instruction and says, okay, I get it. We need to add two numbers. It's the director. It coordinates everything. Then it sends the actual math problem over to the arithmetic logic unit, or ALU. The ALU is the math whiz. It's the one that actually does all the heavy lifting, all the calculations, all the comparisons. And that brings us to the final step, store. Once the ALU has crunched the numbers and has an answer, that result gets written back into a specific address in RAM. And just like that, one cycle is complete. And guess what? The processor is already fetching the very next instruction. Fetch, decode, execute, store, over and over and over. So this cycle is happening at a totally unbelievable speed. But that incredible speed actually creates a problem, a bottleneck. See, the CPU is an absolute speed demon, ready to go, ready to perform billions of calculations, but it often finds itself waiting for the slower parts of the computer to catch up.
This right here is one of the biggest challenges in modern computer design. If the super-fast CPU has to wait for data to make the long journey from the relatively slow RAM, it's like putting a Formula One driver in rush hour traffic. It's just a total waste of power. So how do engineers get around this?
The solution is an incredibly clever trick called cache memory.
So if RAM is like a giant library where you can find any book you could ever want, cache is like the small stack of books you've already put on your desk because you know you're going to need them soon. It's a tiny, personal cheat sheet with the exact info the CPU will probably need next. It's way smaller than RAM, but getting data from it is practically instantaneous.
In fact, it's not just one cheat sheet. There's a whole hierarchy of them. L1 cache is the smallest and fastest, built right into the processor core itself. If the data isn't there, the CPU checks the slightly bigger L2 cache, and then the even bigger L3 cache. Only if it strikes out on all three does it have to make that long, slow trip all the way to RAM. This whole system makes sure that the speed demon CPU is almost always getting fed the data it needs, right when it needs it. So this entire system, the blueprints, the cycle, the cache, it's all been constantly getting better. But the most mind-blowing change of all has been its miniaturization. That's the real story here. That's how we went from computers that filled entire rooms to the powerful devices we carry around in our pockets today.
I mean, look at this. The history of computing is just a story of shrinking hardware. The first generation used these massive, hot, unreliable vacuum tubes. Then came the transistor. That was a total game changer. That led to integrated circuits where we could cram tons of transistors on one chip. And that led to the microprocessor, the entire brain of the computer on a single piece of silicon. And now we're heading into the fifth generation, which is all about artificial intelligence.
And the difference between these generations is, it's just staggering. A first-gen machine like ENIAC used thousands of fragile vacuum tubes. It filled an entire room and it guzzled electricity. Now compare that to a fourth-gen PC, built around a single microprocessor. It fits on your desk, sips power, and is just astronomically more powerful and reliable. That incredible leap is all thanks to one thing: getting better and better at packing more power onto a tiny slice of silicon. The result of this whole journey, this incredible shrinking act, is that the smartphone in your pocket right now is well over 1 million times more powerful than the room-sized computers that guided the Apollo missions to the moon. It's the same basic blueprint we talked about, just executed at a scale that back then would have been pure science fiction.
So we've gone from rooms to pockets, basically by making things smaller and faster. But the next big leap, this fifth generation, is about making them smarter. It's being built on AI, on massive parallel processing, on the ability to actually understand human language. So the question to leave you with is, what new reality is this next generation going to create? Thanks for watching The Explainer.